So welcome everybody to the Heinz Pagel Memorial Lecture Series at the Aspen Center for Physics. As Emily said, Chabachaki from Cornell. The ACP is a truly unique place where physicists can meet, exchange ideas, and stimulate new projects. For example, it's the birthplace of string theory, the birthplace of the archive, a preprint server that has revolutionized scientific publishing. And as Emily said, it's almost completely self-run. It has no large institution standing behind it. This public lecture series is named after Heinz Pagels, who was a well-known particle physicist, a longtime trustee and general member, and also a part-time Aspen resident. And he tragically died in a mountaineering accident on Pyramid Peak in 1988. And after that accident, his family and friends contributed and started this lecture series. Tonight, we are very fortunate to have Professor Ibrahima from Johns Hopkins University as our speaker. He's a well-known expert of string theory, holography, and quantum field theory. Professor Ba grew up in Senegal and came to the US at the age of 13. He went to Lafayette College for undergrad and his PhD at the University of Michigan in Ann Arbor in 2012. After that, he was a postdoc at Saclay outside Paris and at the University of Southern California. Starting 2015, he was a UC President's postdoctoral fellow. Joined the faculty of Johns Hopkins University in 2017, where he's just about to be promoted to associate professor. And the title of his talk today is Black Holes in the Sky and Fundamental Physics. So please welcome Professor Ba.
Okay, thank you for the invitation, and it's good to be here. So the talk that I will tell you, it will be a lightning review on gravity and where our early understanding to some of the main puzzle of gravity today. And this puzzle involves black holes and the fact that now we can see black holes in the sky, and what should that mean? Very good. So since the 60s, particle physicists have been thinking about black holes as trying to understand what we call quantum gravity. But this was mostly theoretical work. What has happened recently, within the last 10 years or so, is black holes now we can see them, we can hear them in the sky, and I'll try to be specific what that means. There are various new detectors that have gone up. There's the EHT imaging, which you've heard some talks over this summer. To sort of give you how important what's happening in terms of gravity and black holes, just within the last 5-6 years, 2 Nobel Prizes have been awarded. The first one on what we call the detection of gravitational waves, which I'll explain, and the second one, which is what's usually called the prediction of black holes in nature, and also some early indirect discovery of these black holes in the center of our galaxy. This is to just give you a sense of how much of a revolution that's happening in physics. Just within the last 6 years, 2 Nobel Prizes have been awarded to this topic. So the big question, which is still lacking, which is a question for theorists like me, is what are black holes? And this is a still outstanding question. Okay. So first, since this is a story of gravity, let me tell you a little bit how we understand gravity and space-time. So it's famously said Newton invented gravity, or in some cases, more specifically, discovered the laws that govern gravitational force. So if we have the sun and the moon, or the sun and the earth, they are pulling each other in a gravitational field. You can ask, what is the equation that tells you how they behave? So Newton discovered that and explained us how it works. There was a big puzzle, which Newton himself knew, which was that how does the moon know about the earth, let alone to know how to move even the earth? This was a big problem, which Newton agonized all the way to his death. And this is called instantaneous action at a distance. So this question was taken up by Einstein. It's also puzzled Einstein for a while. And the resolution is the discovery of what's called general theory of relativity, which tells you that gravity, as we understand it now, we shouldn't think of it as a force, but it's a manifestation of something else, which is a manifestation of a curvature in space-time. So let me explain what this means. What Einstein proposes is that if we have space, you shouldn't think of space as just being static sitting there. You should think of space as something that is more fluid, reacts to what lives on it, it twists, it bends, and it does all sorts of fun things. Famously, there is the Einstein equation, which as we physicists, we have an equation to use it. So on this side, we have what we call the curvature of space-time. On this side, we have taking into account all the energy density of matter that exists in space-time. What Einstein tells us, there is a sense by which these two are equal. If I tell you what stuff exists, it should tell me what space should look like and how it curves. And there is some number that tells you the strength of this relation. More specifically, you can see this in the following way. We have the Earth. You can imagine space and time be some sheet where everything is in. Earth is heavy and it has energy density. It stretches space in a very particular way, as if you have a rubber sheet and you put a big bowling ball inside. What the moon does, the way it knows what to do is see this curvature in space, and it has to move accordingly to move the shortest distance as it can. So this is what Einstein taught us of what gravity is. And this picture, surprisingly, as a illustration, is rather accurate. If you give an appropriately trained mathematician this picture, they should be able to know what to compute and how to calculate things. So one of the immediate predictions of this picture of having space-time and then having energy and matter curve it is that if you suppose take the sun and you have some energy density and you squeeze it and you make it more dense you make it, more curved the actual space-time is, in the same way that if you take a bowling ball, which is heavier, shrink it, it will stretch a rubber sheet more. As this goes, as you make the sun, for example, more dense, what it does, it just creates larger and larger in a hole in the actual space. It just creates a larger and larger curvature. And what could happen if you make it dense enough, there is a phenomena that occurs where you actually pinch off the fabric of space-time, okay? This is a rather dramatic thing. And interestingly enough, this was one of the very first predictions of general relativity. Einstein gave his famous talk at the Prussian Academy of Science on November 25th, 1915. 2 weeks later, Schwarzschild sent him the famous solution, which is the black hole solution, very fast. This solution already is rather interesting. So what the solution effectively predicts is it tells you that if this theory is a correct theory of nature, it predicts this rather dramatic thing where you can pinch the fabric of space-time. And when that happens, as physicists, you try to calculate anything, you will get infinities, okay? So in physics, whenever you write a theory and you calculate, you get infinities, doesn't mean something horrible is happening in nature. It actually means that your picture of nature is not complete. There is something missing, something you add. So rather interestingly enough, the first sort of predictions of general relativity is that it should fail. And this was not appreciated until much later in the 60s, in the 70s, the 60s and 70s, we understood what to do with that. Okay. So one of the interesting thing about this rather dramatic phenomena is whenever, which somehow this theory knows to deal with, whenever you get a solution where you can get such a pinching of space-time, there's something dramatic that happens. There is a horizon that forms. what does this mean? A horizon means that if you are outside here, trying to observe this dramatic thing where you have a hole in space-time, horizon means you cannot see it. You can never see it. And the reason why you can never see such a thing, when that surface forms, it's a surface where light cannot escape. So if you try to shine light and bounce it out, it doesn't come out, right? Any light ray that goes through past the horizon, it can never come out. And whenever a black hole is made, the gravity basically is so strong around this region, around what we call the event horizon, that light, for example, so this picture here is imagining having a dust around the black hole. So the halo that you see up here is actually the dust that is behind the black hole that's emitting light, but the gravity is so strong, the space is so curved that the actual light comes around and comes to the foreground for people to see. So to give you a sense of how extreme such objects are, suppose you take the sun, right, and you squeeze it to the size that it would actually make a black hole. Horizon for that black hole would have a radius of 3 kilometers or 1.9 miles, which is like the diagonal distance of Aspen. If you were to take the Earth and you squeeze it to a black hole, it would have a size that is about 9 millimeters, right? So it's like 1/3 of an inch. So another way to think of it, if you couldn't tell anything about the Earth from outside, you couldn't see it, there's no light. The Earth itself is, from the theory of gravity, is indistinguishable from having a billiard ball that is 1/3 of an inch. And this is an interesting question, which we'll come back to later. One of the fun things now is you could ask, when you go out in nature, do you actually see this dramatic object out there? And the fun thing is black holes exist, and they exist at various sizes. So let's see where they are. First place where we know we should have black holes is when we think about galaxies that we observe out there in the sky. For example, we take the Milky Way. The Milky Way have what's called a supermassive black hole that's sitting in the center. This was observed by Andre Geitz and other people, which won them the actual Nobel Prize. So at the center of the galaxy, our galaxy, there is a black hole. This black hole is very, very heavy. It has over 1 million mass equivalents to the sun, meaning it's a black hole which has a total mass that is equivalent to 1 million suns together. Okay, so when we look out in the universe, we see plenty of galaxies, and each galaxy will have what's called a supermassive black hole. And these are very important in both the development of galaxies and galaxy structure. Okay, and when we look out in the sky, we can see about 100 billion galaxies in just part of the universe that we can see. Already, you have 100 billions of these black holes, whose mass is millions to billions times the mass of the sun. More recently, we tried to observe it directly. This is a famous picture of the M87 black hole. So this was observed by what's called the Event Horizon Telescope, which is a revolutionary tool trying to study things. So these pictures are quite interesting because the hole in the middle is one of the important indications that we have black hole sitting there. Put this in perspective, this galaxy whose central black hole that's being imaged 55 million light years away. This black hole itself has a mass that is equivalent to 6.5 billion times the mass of the sun. These are huge. If you try to ask how big it is spatially, the horizon of that black hole, it has this radius. So to give you a perspective, this is more than 3 times the distance from the sun to Pluto, right? Meaning this black hole is such a dramatic thing you can put this our solar system with the planets 3 times over. Okay, so we know now this thing exists out there in the universe, and there are billions of them. More recently, one of the things we can ask is, let's say 2 black holes find each other, so they would orbit around each other in some particular way. One of the things they can do, so this video not going fast enough, it's fine. But one of the things that they can do, they will orbit around each other. At some point, they would coalesce and collapse and form a bigger black hole. Okay, so this is a rather imaginative thing. If 2 of these black holes find each other, they should move around. They can orbit and then they can collapse each other. Whenever that happens, and as we just described, that we understand gravity and as the fabric of space-time stretching and moving. So if you have 2 very dense things that move around, the way that they move will create waves in actual space-time, similar to having rocks in a pond that you throw, it creates a wave in space-time. These waves, they will travel at the speed of light. And you could ask, can these waves actually be detected, right? If you detect those waves, this is a way to directly see black holes themselves, since you cannot see them using light. So first, what happens when these waves go past us? So if you just are stretching space and time, what happens to the Earth as these waves go by? So here, these are successive crests of the wave as it goes through the Earth. What it does, it literally shakes the Earth in the following way. So let's play this again one more time. There is a bit of lag. Okay. Good. So every time a crest goes, so you can see as 2 black holes are moving, so they're creating, as they are further apart, waves that they create have a lower frequency, but as they get close, they spin about each other. So that's what you see in the last. So you see this very fast shaking of the Earth. But of course, we don't experience the Earth shaking that dramatically. And that's because the amount of change that occurs when this goes past us is 10 with, is 0.1 with 20 zeros behind. So if you take a centimeter, you say, how much has it moved? It has moved by taking 0.1, by taking a point with 20 zeros times 1. So this is the same scale as saying the scale at which you would measure a distance on, let's say, a proton. Okay, it's smaller than that. So the amount of stretching that occurs is very small. So you could ask, do you even have hopes of ever measuring that? There has been a proposal to do this since the 70s in what's called a laser interferometer. So here is a case that suppose a gravitational wave comes through, the Earth is shaking in some way. So this is a picture where you take 2 arms and then you shine a light and then split it between the 2 arms. So as the shaking of the Earth occurs, see that there is the light that bounces here is a wave. When these things move, you see that the waves are going to change. The wave of light that comes, the collector is going to change. Then by measuring the shift of these 2 waves, you can then measure very, very, very small changes on the size of the Earth itself, on the very small distances that would be due to a gravitational wave. So this is an experiment that was dreamed up in the 60s and in the 70s. It took that long to make it work. And what happened, you build this experiment where this interferometer has 2 arms, as we just saw from that video, each of 4 kilometers. You send a light source from here that it goes in 2 arms and bounce, then come back here. And if this arm has shrank, due to the space stretching or shrinking, then you can measure the difference here. You make two of them so that you can make sure that you're measuring gravitational waves. And when you do this, so the first observation occurred September 14, 2015, where it was actually observed a gravitational wave going through the Earth. Interestingly enough, the frequency of this is in the audible range, so you can actually hear the gravitational waves. So here, let's play it again. You can listen to it, and what you hear is the frequency changing as these two black holes are orbiting each other. They're coming close. There's a pitch that goes up when they come very close and spinning very fast. And the beep that you hear in the end is exactly that. This is a rather revolutionary observation. So to just tell you the details, this is an observation of two black holes that are colliding. Each one of them has a mass that is 30 times the sun. The other has 35 times the sun. They spun around each other and then collapse to make one single larger black hole. The amount of radiation that was dumped to just wiggling space and time is equivalent to taking the whole sun, taking the three times the mass of our sun, using the famous E equal to mc squared, is that amount of energy that was dumped all at once. And because of that, these two black holes, they are at a distance of 1.4 billion light years. So this is a wave that's been traveling for 1.4 billion light years to reach us. We're able to finally see it. So this was the first direct detection of actual black holes out there in nature. And what has happened since then is that LIGO worked rather incredibly well, right? And then we've observed hundreds of different collisions of black holes that merge and make bigger black holes. So in these two diagrams, you would have one black hole merge with another to make a third. We have observed hundreds of them, okay? More interestingly, we also observed the collision of what are called neutron stars, which are these ultra-dense stars made from neutrons themselves. This sort of image is rather exciting. So this sort of extreme thing, which was predicted a long time ago, now we can see them directly in the sky. We can just, and we see hundreds of them, not just one or two, that you might guess. And unlike the supermassive black holes that we just talked about, these black holes have masses that are about 20 to 200 masses. Even more excitingly, very recently, in a rather very clever experiment done by using the Hubble telescope, people were able to observe a single black hole just moving in the Milky Way directly. Right? And the way that was observed is, as we said, that gravity bends light. If there is a sun sitting here and you put a black hole sitting here, and your black hole is just moving in this way, because it has such a strong gravity, it will bend the light of the sun that is behind. If you're watching it as the black hole is moving, there's a lensing effect where momentarily the sun gets brighter and then becomes dimmer. So in a very clever observational methods, which actually took since the 90s, people were trying to do this, people were able to just see in the sky a freely floating black hole, which has 7 times the mass of the sun. This is very, very recent. Okay. So from all of this, you conclude something rather interesting. So after LIGO is updated, it will be a detection of thousands of more of these black holes. And as we move forward over the next couple of decades, there will be new of these detectors. There's LISA or ELISA, which will be in space. There are next generations of these interferometry detectors, which will have longer arms, and these will start to see millions more black holes in the sky. And all of this is very exciting because it's the dawn of a new astrophysics. To put this in perspective, right? Ever since humans can look up in the sky, the only way we could learn about anything in the universe by looking and seeing light come in. All the telescope technology that exists so far is to collect light, whether it is in the visible range or in other ranges. This is the very, very first time we have a fundamentally new window of actually observing the universe since the dawn of man. This is the first time where we have a whole new way looking out in the sky and seeing something about the world. Okay, so this is a start of new astrophysics, new astronomy, very exciting times. Motivated by his result already, there are many new ideas to try to think about other ways you might detect gravitational waves themselves. The conclusion that comes out of all of this is that black holes went from being these rather esoteric, fairly theoretical thing, actually being objects that we expect out there in the universe, and we expect them to be as ordinary as stars. Okay, so there are many, many, many black holes there. So from this point of view, the big deal that we don't know what they are. Okay, and we don't know how to think about them or how to describe what is behind the horizon. So the rest of this talk, what I will try to do is try to explain the fact that we see black holes. Why is it a rather serious problem, and what it tells of how much we know about things that can exist in the universe. This leads us to what I will call black hole thermodynamics. Any questions? Okay. So one of the interesting things about black holes that someone like a theorist like me would study is you can think about these and ask, how do you describe them? In Einstein's theory of general relativity, to describe a black hole, I just have to give you three numbers. I need to give you a mass, how heavy it is. I have to give you a charge, if it has any sort of a charge. And I have to give you an angular momentum or tell you how it is spinning. So the way you should, so that is already surprising. Here's why it's surprising, okay? Take a human being, and I tell you basically the clothes that he's wearing, and I tell you how heavy it is, how heavy they are. That is very far from telling you anything about the person, okay? I need so much more to know about a person or anything in the universe. If I want to talk about this piece of wood, I cannot just tell you the dimension and tell you about the wood. I need to tell you a lot more things. So black holes, in general relativity, are very pure. If I just tell you those three numbers, I know everything I want to know about them from the theory of gravity. It's as if they are fundamental particles, the point of view of general relativity. So they're very, very pure. However, you can try to study what a black hole does, right? More specifically, you can try to study what the horizon does. Does it have any interesting physics? You can ask, if you throw stuff on the black hole, what happens to the horizon? If you throw something that has a spin, what happens to this black hole? So this game you can play and try to think about more properly. And something revolutionary that was discovered was that there is a sense by which a black hole is something thermodynamic. Let me try to explain what that means. If we think about the air in this room, the way we learned early on to describe the air in this room, give you the volume, right? The space it occupies. Give you a temperature, which tells you something about the air in the room. And I give you the pressure, okay? So these are the three numbers that I can give you, and it tells me, the air in this room and what it does. Okay, so that's what we mean by thermodynamics. These numbers that characterize something large. But of course, we know the air in this room has many more features, right? We know that they're made of air molecules that are flying around. cannot see the air molecule, but we know that that's what they're made of, right? It took actually a very long time before we understood that the air is made of molecules. People won Nobel Prizes for this, and physics have been revolutionized various ways. Before we knew about air molecules, right, I would use temperature, pressure, and the volume to think about the air in the room. It turns out you can associate quantities like that for a black hole. The gravity on the horizon, meaning the strength of gravity on the horizon, something like 9.8 meters per second squared, behaves like a temperature. The mass of the black hole, not surprisingly, is like the energy that is in it. And then how it spins tells you the equivalence of a pressure. But there is one sort of important parameter that appears, which is what's called an entropy, right? So in thermodynamics, the air in this room has entropy, okay? And I will try to explain what that means. For black holes, the area trying to behaves like an entropy. This is a very important fact, which is what we will try to understand for the rest of this talk. Let's try to make sense of entropy. So entropy, for example, in this room, is a way of telling you how much stuff is in this room, is a way of telling you about the properties of the molecules that make up the air, okay? So entropy, you think of as measuring degrees of freedom. It's a number, and it's a number that tells you how many different ways I can label the various molecules in this room, okay? So think about each molecule moving around. It will have a velocity, will have an orientation, right? So I can give a label for that. So let's say now I go and I list all the different molecules that are in the room. For each one of them, I have to tell you which direction it's moving, how it is moving, and which way it's pointing, okay? You collect all of that, all of those numbers, what we call the entropy, right? The entropy tells you the number of ways you can label the individual degrees of freedom of the air molecule sitting here. Another way to say this is that the entropy is telling you about the information content of the gas in the room. Okay, a single bit of entropy is what we call a single unit of entropy is what we call a bit. Right? In computer science, if I have, if I give you a computer and I ask you what is the memory, I tell you how many megabytes it has. So what that really means is that the amount of data it can encode. Another way you can think about entropy is telling you the amount of data that you need to encode a system. And a computer is telling you the amount of data that you need that you can encode within the computer. So it's a very useful and powerful object that allows us to talk about how much stuff is around. It's a way of telling you how much stuff is around by telling you how much information I need to label everything. So what turns out to be the case is in black hole physics, there is in this analogy, so this is the first formula that I'll show, there's a notion of entropy, and the entropy is given by the area of the black hole. Right? Somehow the area of the black hole is telling you how much information this thing has associated with this. And we can calculate it, and it is going to be some large number. Usually we write it in units of the mass of the black hole, where we give you how many times heavier is this black hole times, let's say, the mass of the sun. That's a good way for us to write this thing. Okay, so before I sort of try to tell you a bit more about this, about at least for our physical world or the black hole that we observe, you can ask a different question. Since entropy is telling you about the information, the amount of stuff, it's a measure of stuff that exists, there are various places where we can try to calculate it, for example. In this picture, imagine we take all the stars that we can see in the universe, all the stars that we can see in the universe that are made up with all sorts of hydrogen and everything about it. You can associate an entropy to that, which is telling you how much information or encoded in that. Or said another way, if I were to take a computer, try to code every single star, all of the physics associated with them, the whole universe, how much data I would need is given by the entropy. We can calculate it, that is, by some large number, 10 to the 79. Another thing you can also do in the same way, you can imagine taking all the dust, right? There's much more dust and gas in the universe than there are actual stars. You can actually also ask, what is all the entropy associated to that? You can give that, that's 10 to the 86 units. Another entropy you can also try to think about is the cosmic microwave background, which is the afterglow of the Big Bang. And you can ask how much data you would need to encode the physics of that. Okay, so that's also another very large number. And then you can go on. There is other things that we call neutrinos, which you can also calculate what the entropy is. So all of this just tells you the size. It's a way of telling you the size of the computer that you would need to describe physics of all of these things. So you can then ask, with the formula that I showed you for the black hole, what happens if I take the black hole at the center of our galaxy and calculate the entropy, right? Which is telling me how much stuff it should encode. So you can calculate that, and it's 10 to the 90. What does this number mean? This number means is that just by looking at the single black hole at the center of our galaxy, it requires more information to describe than all of the known stuff in the universe, right? This is the sort of perspective that you should have, why black holes are important. There is so much more information, so much more new physics inside there that we don't know, we don't yet understand. But to put this more in another perspective, we can do accounting. So Milky Way, as we just described, has this huge amount of entropy. If we collect the entropy in the observable universe associated to all of the lights, all of the neutrinos, dark matter, if we say dark matter is made from some cold, heavy particles, you get this. Somehow, just at the center of our galaxy, there is more stuff from the point of view of entropy than there are in all of the observable universe. But now we take this to another level. How many galaxies we observe? We observe trillions of galaxies, 100 billion to a trillion galaxies in the observable universe. Each galaxy itself has a supermassive black hole, which has a mass that is 1 million to 1 billion times the mass of the sun. So what this tells you is that if you collect the entropy in all just from the supermassive black holes, never mind the smaller ones that we can observe via gravitational waves and various things, that this is a very large number. Tell you another way, there are 100 trillion times more bits of information behind black holes than all of the observable matter and energy in the universe. This is dramatic. So the fact that, or you can say it another way, if you have a supercomputer, you're trying to simulate the whole universe, most things, your whole computer, all it will do is just try to simulate what's behind black holes. Okay? So the big problem now is the following, that as of now, our understanding of physics cannot tell us what is happening behind black holes. So this is the central problem to understand where all of these new degrees of freedom are coming from. This is a big problem now in physics, and it becomes more urgent, at least in my mind, than anything else. One place that we've been looking, for some of us, we've studied string theory, and we can use string theory as a way of trying to understand what these objects are and what these new degrees of freedom are. And the fact that now, as I showed you earlier that there are new ways of looking out in the sky and observing black holes. You could ask whether any of these new stuff that we don't yet know and show up in the sky allow us to actually learn something new about physics. Okay. So I'll stop here, have more. People are curious, but I think this is a good place to stop and start to take some questions.
Oh.
Yeah.
Nice. So let's start the Q&A, please, over there.
In the example you gave about the black hole that was measured, the light coming in 1.4 billion years, we have no way of knowing if it still exists, right? And do they disappear? I guess this would be my follow-up.
Okay, good. So the question is, in the example where you have the gravitational wave collision of two black holes that is at 1.4 billion light years, which the time it took for the light to get to us, does that black hole still exist? That's the question. So first, black holes can decay. They have a decay process via Hawking radiation. That black hole is so big, so the decay, the time it takes to decay goes as the mass cubed. It's a very, very long time. The time it takes for that black hole to decay is much, much larger by many folds times the lifetime of the universe itself. That black hole is still there. It might have collided with other things, but for all intents and purposes, that's there. Do we know its physics beyond that? We can't say that yet. Why is exciting?
You say there are massive black holes in the center of galaxies. Is there a causal relationship between those two, or which came first?
This is good. This is a very, very interesting question. And so the question is that we know that there are black holes at the center of galaxies. The question is, which came first, the black hole or the galaxy? So this is not my field of expertise. I'll try to answer. So the question of actually galaxy formation is a very much open question. So do you make a black hole first and then things fall, or do they come together organically? Right. So I don't know the exact answer to that. But one place that we know we look at that help where you can see black holes grow is what are called quasars, right? Where you have matter that collapse and make a black hole, and part of the growth of the galaxy itself involves the black hole devouring a lot of matter, and at some point it has to stabilize, give you and shuts off and gives you this feature. So typically the black hole is about factor of 10 times lighter than the actual total mass of the galaxy. It is needed to actually form the galaxy itself.
Oh, if light is coming out of black hole, what's the difference between whether it falls in or goes around, like in gravitational lensing?
Good. So good. So the question is, if light is if light is going around the black hole, if I understand it correctly, there's a difference between light coming out of a black hole or light going around the black hole.
Well, why doesn't it fall into the black hole?
Good. So why doesn't the light that's coming around not fall into the black hole? Good. If we have a black hole sitting here, the gravity is very strong that if you have light, say a sun is sitting here and it shines light, if it gets very close, it sort of bends around, right? It just like it's a slingshot effect. The question is that if, let's say this is further out, it will go, it might get deflected. If it's a little bit closer, it will go, but then it might slingshot thing. The point is that the closer it is, it can come very close to what the black hole is, but there is some radius where if it comes close enough to that radius, it will just fall in.
Is that the event horizon?
That's not the event horizon. That's what you call the light ring. So this is an excellent question, because what the light ring is, if we go back with me. Let's have a better picture, sharper picture from more recent data. Let me show you that. So this thing is what you call the light ring. It's very interesting in the current observation of, in the way we're observing black holes, because so this radius, we have the event horizon sitting here. Anything that goes into the event horizon cannot come out. Then you have this light ring where anything that sort of comes outside of it is going to be slingshotted. Things that come very close and touch the actual light ring then go around the black hole, like the moon going around the sun. So you can actually have light orbit a black hole. But these orbits are unstable. Thank you, Siri. But these orbits are unstable. If it moves a little bit, it will fall in or fly off. But the fact that you can have, you know, stars all around, shining around, means that this is a surface where somehow light can stick around, go around, then come out, or go around for a while, then fall in, is what's responsible of getting these rings, which we call light ring. These light rings are actually very interesting in studying black holes, and is what the EHT did is observe this light ring. The space inside that is dark, you cannot see light come out of it. You cannot see this light because that would correspond to things falling in. But this is still is not where the horizon is. The horizon is even somewhere further inside. You could actually see, so since you asked this question, there's another place where you can already observe that there is this special surface of the light ring is here. If we play this video here, I don't know whether you can see it very well. It's rather clear in my computer. There is this sort of line over here, right? In this simulation, this is also the light ring associated to these extreme things. One of the interesting about this light ring is that, as you see these two black holes coalesce, you can see that there's a lot of fluctuations happening on the light ring. Even when the black hole settles down, there's activity happening along that light ring. That activity is actually part of the wavefront. That activity will have information about the physics of this. Could have, one of the hopes of many of us, for me, is that studying those things will have information about what black holes can be.
Earlier, you had space-time depicted as a plane. What occurs on the other side of that plane?
Good. So the question was earlier. I had a picture where. So let's go back to it. Here, where I've depicted space-time as a plane. So this is because I'm artistically challenged to depict three-dimensional space that I'm actually living in and see it. So here we depict it as a sheet, just sort of give an indication that you get stretched. But instead, you know, I'm a heavyset guy. I'm standing here. I'm curving all of space towards me, right? Stretching in all directions towards me. So that's what that indication. So, and it's just not space, but also time in a particular way. And time is also stretched by energy density. And that is actually quite important for GPS technology.
For a given mass, would a spinning black hole be larger in diameter?
So the question is for a given mass, and I make the black hole spin, is it bigger or smaller? Good. So if I have a black hole of some mass and I give it spin, it actually shrinks. Smaller. A spinning black hole with the same mass it has a smaller radius. This we can calculate.
But centrifugal force would make it bigger, so.
Good. So the question is whether the centrifugal force would make it bigger. The centrifugal force doesn't make the horizon come out. That's what you're asking it actually. The radius goes down.
What is the concept of a singularity in curvature?
The concept of a singularity is from the point of view of the curvature. You write down the curvature and you try to see what number it is. It's literally infinite. So that just means that theory has broken down. So whenever we hear singularities in physics, they might sound, you know, fancy or so forth. But singularities in a physical theory you don't want. It's actually bad. That tells you your theory has broken down and you need to do something else to fix it.
Going pure theory, assuming we're flatlanders.
Okay.
You know, in a less sober moment, explain what in the world's going on. What's on the other side of a black hole? What is the correlation of black holes to suns or celestial bodies?
Good. Okay, so the question is, from, you know, down to Earth, what is behind a black hole?
If we're flatlanders, we can't see it. We don't understand it.
So good. So in a sense, the term black hole is literally, as it is, the sort of an indication of something that we don't know. We cannot say we understand the physics of what is happening behind the black hole because we don't know. And part of the showing you the entropy is to show you that, you know, the physics that we know not generate large entropies of that. We actually need new physics. We need new science to understand what it is. So I cannot answer that question. Well, I've been working on it. There are other, you know, there is Kaylin here who's been working on it since probably younger than me. But this is a question that, you know, this is the generational question in my mind. You know, before it was just a theoretical question. Oh, you have black holes. What could they be made of? Now we can see them. It's a real physical problem. It just indicates there's actually real, there's very important chunk of the universe that we cannot understand. We don't have tools to make sense of.
One more last question over here.
Or are you using string theory to that end?
Good. So string theory is a fantastic playground. It's a fantastic world. And string theory is a theory of gravity itself. It's a theory of gravity which can tell you many more ideas. Within string theory, you can find new degrees of freedom that are not like the molecules or made up from the stuff. New objects which can actually make black holes. So in string theory, you can build a black hole from ground up. And in building so, you know exactly what are the ingredients that went into making it. And in knowing what the ingredients that went into making it, you can actually see in the same way here, you know, once you know that there's air in the room, you can use the air molecule to calculate the entropy. In string theory, we can also do that. Then you could ask, can I use those objects and actually try to build something that looks like a black hole? So part of my work actually have been doing that. These are these fancy pictures that is in the program. So I will just show these and then we can call it a day. One of the things that we were able to understand or able to show is in a very idealized setting, use some of the ingredients in string theory, try to see whether we can make a black hole that looks like, make some object, you know, something that would be like the air in the room that very far away would look like a black hole. Okay, so we can use this. So this is important because if we can do things like that, and we can we'll be able to know what can gravitational waves or imaging technique tell us about what these things are, right? It gives us an example of prototypes which we can test against. So this is what these pictures that you see. We had constructed these new objects here using string theory, and we can calculate everything about it. So in this picture, what we say is, suppose you have a black hole sitting in front of you. Let's maybe do this one. This one might be better, right? Suppose you were to have either a black hole or one of these things that we can calculate from string theory sitting here. There is light coming behind, which is the sky. that patch of the sky looks like this. So this light is coming. Exactly as was asked earlier, light from behind is going to bend as it goes around. So then here is an example of if you were to put a black hole in front of you, so the light that bends, basically this is this picture we just described. This would be like the light ring, okay? And then everything else around the space is curved, so the light that's coming at you is curved. So these new objects that we were able to come up with, they are far from being anything physically real, but they are very good prototypes to start with. In which one of the things that you observe is you can start to compare them. They're very compact, so they will have, there's a region here which looks like the light ring. So if you compare this image compared to this one, outside looks very much the same. And the radius that differentiates this is what we call the light ring. However, because this thing is like a star, something is stuff sitting there, some light can go in, it will dance around and at some point come out, right? So in these constructions that we have, which they are really like prototypes of trying to understand what could be behind the black hole, what it will allow us to do is to understand more sharply when we get the data, let's say LIGO or other imaging things, what should we look for in there to tell us whether there is new physics or not, okay? This is one way string theory helps us. And the reason why we can get there is because we know string theory can generate the counting we want. So there is to just compare the black hole versus something like this is, in a recent paper we wrote, is this, like you can see various features that helps us understand and learn these things. But that's just one way you can use string theory to try to understand black holes.
All right, let's try.